All right, here we go. Welcome to lesson 7.5 geometry notes, properties of trapezoids and kites. So we'll wrap up chapter 7 here, look at a couple new types of quadrilaterals, some properties, ways to show a figure is, a trapezoid or a kite, and look at some algebraic situations where we may or it may ask you to find a side length, an angle measure, that type of thing. So let's get it going. Make sure we're adding this stuff to our notes. So here we go. Trapezoid. What is our definition of trapezoid? So quadrilateral, four sides with exactly one pair of parallel sides. So it's kind of hard to see here, but I'll put, we should end up with one set of parallel sides. So it's almost like we're backing up a little bit as far as on our food chain, our hierarchy. We've talked parallelograms, squares, rectangles, rhombus so far. This is as least specific a quadrilateral that we've ever seen. We started with parallelograms. Well, that had at a minimum, it had to have two sets of parallel sides. This is kind of backing up and saying, oh, all we need is one, and then we can call it a trapezoid. All right, so that's what it is. A little bit of vocab that goes with it, so kind of parts of a trapezoid. If you wanted to set your notes up in class, we did it where we just kind of drew arrows to each part, and we can do a little bit of that here in these notes as well. So if we're talking about the bases, we're talking about the parallel sides. So there's two bases here. I don't want to go crazy with my arrows. It's going to get a little cluttered, but those would be your bases. The parallel sides is what we would call the base of a trapezoid. And I'm going to jump actually down here to where it says the legs, because if we're talking about sides, the parallel sides we're calling the bases. The non-parallel sides, so here's where it gets kind of tricky because my stuff starts to overlap, but my non-parallel sides we would call the legs. Okay, so our legs are there. So like I said, if you want to make just a big picture and kind of draw the arrows there and say legs are the non-parallel sides. And then we end up with two different pairs, so two pairs of base angles. Okay, so maybe we number them here. So angle 1 and angle 2, that would be a pair of base angles. And then we've got a different pair, angle 3 and angle 4. So obviously 4 interior angles, but when we start, kind of talking about partners and stuff like that, a base angle pair would be one that forms an angle with the leg and a base. All right, a leg and a base. So we've got a pair here and a pair here. Not a ton of properties like specific, just because we've backed up, we've taken away the other parallel side, that we lose a lot of the properties we've talked about. So opposite sides aren't congruent anymore. Diagonals aren't congruent or perpendicular. They're not angle bisectors. All that stuff is specific to the figures we've already talked about. So you lose a lot. Really, the one thing going on here is that we still have parallel lines. So you can see on the bottom here, we added a one property of that consecutive angles between the bases are supplementary. So what does that mean? That means basically like angles 2 and 4 would be, without knowing anything about their numbers, I could tell you that angles 2 and 4 are supplementary. And we would also know that angle 1 and angle 3 are supplementary. So between the bases, we say that angle pair would be supplementary. Nothing with 1 and 2, though. I don't know 1 and 2 are the same. I don't know 3 and 4 are the same. But I could jump and say 1 and 3 are supplementary, 2 and 4. Okay, where is that coming from? Really, it's coming from going back to a few chapters to chapter 3 that said, hey, when we have parallel lines and we sketch a transversal, we're basically working with throw some numbers in there. Angles 2 and 3, those are consecutive interior angles. Those end up being exactly what we're talking about, because all I really need to do at this point is connect my parallel lines, and look what we got right there. We've got a trapezoid. So that's kind of what's behind it there. It's not, I wouldn't say it's really a new property, but definitely applies to a trapezoid. So there we go, trapezoid. What it is, one kind of property that we'll do it, or we'll need to know, and then some of the vocab associated with it. Okay. All right. You can, I would say, maybe put this in just a separate section because it's different. That was kind of just specifically focusing on what is a trapezoid. This is kind of like a segment within a trapezoid. So maybe looking here as just like a separate section into what's called a mid-segment of a trapezoid. So pause, add the definition. It's the mid-segment, or I'm sorry, the mid-segment is the segment that connects the midpoints of the legs of a trapezoid. So if we've got a trapezoid, which we can mark here and say, hey, okay, this is a trapezoid, and I connect the midpoint of this leg, we're indicating it's the midpoint by tick marks there. We're going to indicate that this is the midpoint of this leg. I don't know, so you can tell, or you can see I'm using different sets of tick marks. I don't know. I mean, I know this picture kind of looks like it, but I don't know, like this piece right here and this piece right here are congruent. So I'm going to use separate sets of tick marks to indicate that. But this, let's see, let's highlight it here. This pink segment is what we would call the mid segment. All right. So kind of a feature of, or a part that we could add to a trapezoid. All right, and then that segment itself actually has a couple properties that we should know or should be aware of. Whoops, meant to close that there. So two of them, and kind of short and sweet. I think we can add them right here. So the mid segment of a trapezoid, one is always going to be parallel to each base. So when we, this is a pretty good picture. It's very similar. It's got some points on there that we could kind of talk about. M segment, MN would be the mid segment, but that's been added now that MN is parallel to both AB and CD, as well as MN lengthwise. Its length this is kind of a fancy way to say it, is 1/2 the sum of the base, or the lengths of the bases. I would say it more as, that's an easier way to say that, is the average of the base lengths. So there's, that's half the sum of the lengths of the base is probably the little bit more formal way to say it. But basically it's the average length. It's kind of right in between. So if this top base here, A segment AB, was 10 units long, CD was 20 units long, I could average them. 10 plus 20 is 30, and I divide it by 2. This is 15. With numbers like that nice, we could say what's right in between 10 and 20? 15. So there's different ways to kind of think about it as far as that second property. But two things we need to know about the mid segment. So what is it? Connects the midpoints of the legs. And then two properties of, it's parallel to the bases, and it's the average length of the bases. Okay, so this next example is kind of an informal one that I just kind of put together. It's maybe should be worded a little bit better here. So we've got a figure, trapezoid ABCD. Okay, we're told that segment EF is the mid segment. It should say mid segment of the trapezoid. And it's basically asking, you can kind of see with the question marks, what is the length of segment AD? What is the value of X? What is the value of Y? So let's take a look. Obviously, sketch the picture. Pause it, give them a shot. I don't think these are overly tough, although X could potentially give some people some trouble. So let's take a look here. Because it's the mid segment, we're told here that EF is the mid segment. There's certain things that I can add. I could add this information that it's parallel, right? That was the one property said, hey, it's parallel to the bases. So I could add that just to remind myself that it's parallel. I also might want to add, like, hey, the point E is the midpoint of segment AD, so it's not going to hurt me to put some tick marks there and there. And then F is also the midpoint of segment BC, so BF would have to be congruent to CF. I don't know if all that information is necessary, but that's basically what's going on there, and other things that I know. So I think when I look here, when it asks us for, let's start with the length of AD, just kind of knowing, hey, I've added some markings here. AE is congruent to ED, and I know ED was 5 inches long, so I can say that AE is also 5 inches long. So the length of AD, when I put those two together, would be 10 inches long. So not bad. That really just kind of stems from knowing what the heck is a mid segment, connects the midpoints. Let's dive into, maybe let's do Y. I think we'll come back to X. Y is more properties of parallel, I was going to say, almost said parallelograms, of parallel lines. So being able to kind of move around, I've got 3 sets of parallel lines, and if I kind of treat this, so see if you can follow me here. We've done this in other chapters as well, where I extend maybe my parallel lines and treat this as a transversal here, and just kind of see what's going on. I know there's different ways to kind of get there. We end up with this 95 degrees down here. I'm able to move that number around a little bit. Like that would have to go there. Why? because the corresponding angle postulate says when lines are parallel, corresponding angles should be congruent. And for the same reason, I could also say that this, I guess I could name it, but we'll just mark them here. Those two angles right there would have to be congruent because those are also corresponding angles. So what are we thinking here? I'm thinking, you know what? If you kind of step back, and maybe I did more work than I had to do, if we just focused on this entire quadrilateral ABCD as one single trapezoid, we could almost go back to our one property of a trapezoid and say consecutive angles between the bases. So now I'm talking about the Y and the 95 have to be supplementary. That might be all I need. Okay, so this 95 here, and this Y should be supplementary. That was our one property of a trapezoid that we said has to be true. So basically 95 plus what equals 180 degrees. I think we're talking about 85 degrees. When it's all said and done, Y should be equal to 85. So hopefully we followed there. I didn't mean to. I was kind of just, I didn't really think about it too deep, and all of a sudden it was like, you know what? We could have got it right away off the one property of a trapezoid. So there we go. But we could have also jumped to 95 here and said, hey, you know what? Same way 95 and that 95 and that Y are also supplementary. So different ways to get there. All right, last one. We did say with the length of a midsegment that it's the average length of the two bases. In the kind of the simpler example I said here on this one as well, if this is 10 and this is 20, this has got to be right in the middle, 15. Now, what the little curveball here is, okay, well, this is X and this is 11. This 18's got to be right in between whatever 11 and whatever X is. So I bet you there's a lot of people that can kind of almost guess and check or just kind of logic their way to, well, this, it's basically 18. I have to go down 7 to get to 11, so I must have to go up 7 to get here, which is going to be the case. I'll show a little bit just so we can see it in case they do get tougher. I could more formally say, you know what, if I take X and add it to 11 and divide by 2, why divide by 2? Because that's how you average two things. So I'm taking, hey, you know what, let's take this base and add it to the length of this base and divide that total by 2, and that's going to give us the average of those two bases. We know that number should come out to 18. So I'm showing a little bit more formal way to kind of think about this, just in case, like I said, potentially this could be 2x, and maybe this is whatever, x plus 3 or something like that. So all of a sudden, all these x's show up and it's like, what? Now how do I solve this? So I just want to give us an option to do it a little bit more algebraically. So to solve this, I would multiply both sides by 2. I'm going to cancel and say x plus 11 equals 36. We'll subtract our 11 and get x equals 25, which we said, hey, you know what? That kind of that informal way of back to the original that was here, 18, which is what it should be. I should get this out of here. I don't want to confuse anybody. Hey, 25. We went down 7 to get this way. I bet you I have to go, if I'm going to average, if this is right in the middle, I got to go up 7 to get that way, so 25. So long story short there, x equals 25. I think we're okay. A couple of them there. I didn't mean to drag out any longer than we had to, but I at least wanted us to see potentially maybe using some algebra a little bit more formally to find an unknown there. Okay? All right, so there's an example of something I might ask you to do with the midsegment and some of its properties. All right, let's keep it moving here. Next figure. So there's actually 3 figures. I know the name of the lesson was properties of trapezoids and kites. So we're thinking, oh, I'm going to get by with just 2. There's actually a second type of trapezoid, which is right here. It's what's called an isosceles trapezoid. So it's a trapezoid, so it still falls into that family, but it's a specific type of trapezoid in which now we've made the legs congruent. So the parallel lines, this is what makes something a trapezoid. And now that we've indicated here with the tick marks that, yeah, these non-parallel sides, they're also congruent, that's what makes us an isosceles trapezoid. All right. I think, I've got the properties here. Maybe let's just do the properties kind of how we would have done it in class. We'll do it right here. So let's look, let's go properties of. So the first one, and there's two of them really, is that the base angles are congruent. Okay, so each pair of base angles would be congruent. So I think we can do a little picture here, and we'll just eventually slide down the screen here. But if this is an isosceles trapezoid, which I should show that, okay, hey, now it's officially an isosceles trapezoid, we would know that this angle right here is congruent to this angle, and we would also know that this angle is congruent to this angle. All right. There's still supplementary between the bases, so the pink plus the purple would still add up to 180. Their measures would still add up to 180 going this way. But this new property now is only of isosceles trapezoids that this pair would be congruent and this pair would be congruent. Okay. That's actually also a way you could prove a figure is an isosceles trapezoid. So we're going to add that here because a lot of what we're doing in this chapter is how do I show something, how do I show one figure as another figure? So we'll kind of add that that's the property of, is that base angles are congruent. Let's just write the converse right away. If base angles of a quadrilateral are congruent, the quadrilateral must be an isotrap. That's our abbreviation there. We can shorten that up, isosceles trapezoid. So the types of questions we've been seeing lately have been, I give you a quadrilateral, looks like a square, right? And well, right now it's nothing because we don't have any markings. But if all we know is I've got a congruent angle pair here, and I've got a congruent angle pair here, and I say, tell me what that is. What does that have to be? That's enough for me to narrow it down and say, well, that's got to be an isosceles trapezoid. So just based on the markings, that's what it should be. So how do we get there? Well, any parallelogram's off the table, right? Because opposite angles are not congruent. So it can't be a parallelogram, which rules out rhombus, rectangle, and rhombus, rectangle, and square. So for now, is okay. Well, is it trapezoid or is it isosceles trapezoid? This is only true in isosceles trapezoid. So that's a way to show something is an isosceles trapezoid. It's kind of turned on its side, but it's consecutive pairs of congruent angles. So that might raise the question, and I'm going to erase this here, but could you make the argument that right there is an isosceles trapezoid? Potentially, a lot. To be completely honest, it really depends on the context and the setting you're talking about. Because you could argue that, hey, I'm treating these as two separate entities. Here's a pair of congruent base angles. Here's a pair of base angles that are congruent. So this has got to be an isosceles trapezoid, and it would actually still have the features. Is this parallel to this? Sure. Is this congruent to this? Sure. We know more there because this would obviously have to be a rectangle. So I'd get some other information going on here with this parallel to this. So I don't want to throw you for a big loop or anything like that and say, is a rectangle an isosceles trapezoid? Does that fall into that category? It kind of depends on who you're talking to, who you're asking. For now, we'll kind of just keep them separate, but based on that, the green there, that yeah. So, anyways, no, I don't. I'm sorry to confuse you. That if we see a marking like this, I should say isosceles trapezoid. All right. I promise you a second property. Let's take a look here. Hopefully, you're following along. Second property is diagonals are congruent, but don't bisect one another. All right, so we've seen the diagonals are congruent. That is true that's a property of both a square and a rectangle. But in both of those figures, the diagonals also cut each other in half, bisect each other. And that's different in an isosceles trapezoid. So let's do the same thing. Let's make a little picture of an isosceles trapezoid. Okay, sure. Isosceles, that's trapezoid. Now it's isosceles. If I were to draw or sketch in my diagonals, okay, not terrible. I would see, hey, yeah, those are the same length. but this is clearly not the midpoint of the diagonals of each diagonal, right? So just the way it kind of looks, this part right here looks shorter than this, and this part looks here, right here looks shorter than this. But in the end, yeah, I think we've hit this right here. The diagonals. How long is this diagonal? Well, it's 3 total tick mark segments. How long is this diagonal? It's 3 total. So they are, yes, the same length, but not the midpoint anymore there. Okay. And it turns out that's actually another way to show that a quadrilateral could be, or would be, an isosceles trapezoid. So let's say it like this. We're just kind of rewording it, but if diagonals are congruent but don't bisect one another, the quad, so we'll just abbreviate the quadrilateral must be an isotrap. All right, so that still kind of comes back to that same, I'll put that on there so you can, well, you can obviously pause it, but so the same type of deal there where I give you something that looks, it's just a generic quadrilateral, kind of looks squarish, but right now it's quadrilateral. We start getting information. This time we get information on the diagonals. Now the way it looks right now, it looks like they're identical, right? It looks like they bisect each other, but I got to trust my markings and say, let's say we get this, this set of markings. Are those diagonals the same length? Sure. It's got if we want to be informal, this has got a pink and a red. This diagonal's got a pink and a red, or pink and a double red, pink and a double red. From here to here is the exact same length as that. So that's the diagonals are congruent part of it, but they're not cutting each other in half, which would be, that's the bisect part of it. So yeah, this would have to be an isosceles trapezoid, right? And it couldn't be a square because these would be identical. It couldn't be a rectangle, same thing. So there you have it. Don't describe it. I'm throwing stuff out there, but I've seen it described as the left half of this diagonal is longer than the right half of this diagonal. Like this is the best way to say stuff. Use the phrases and the terminology that we're using in class. Okay. So there we have it. There we go. I think that's what we need to know. We've covered what we need to know about isosceles trapezoid. So what is it? And the 2 properties and ways to show or prove a figure is a trapezoid. If you're asking, and I just kind of dawned on me here, did we cover a way to how would I show a figure is a trapezoid? So I know I'm kind of backing up a little bit, but could I show that this is a trapezoid? Really, what we would have to show, we'd have to use CIA converse. I'm going back in the old archives here, converse theorem, and I know I'm jumping a little bit, but to show parallel lines or parallel sides. So what would we need to see to say like, hey, this has to be a trapezoid? I'd have to look at, I need information. If I knew that this was a 130-degree angle and then I knew this was 50-degree angle, that would be enough to say, okay, hey, this must be a trapezoid. I wouldn't necessarily expect us to dig deep and grab that CIA converse theorem. Even saying something along the lines of those consecutive angles are supplementary, which makes this line parallel to this line. Okay, that's enough to say that that's got to be a trapezoid. Another common one, without even numbers, would be something, I see 90 degrees and 90 degrees. The common mistake for both of these is that people want to say, hey, you know what, these got to be parallelograms, squares, rectangles. This one right here, that's kind of tricky because we see the 90 and 90 and we think, oh, square, rectangle. But what does this mean? This is 90 and 90. That means these are supplementary, these 2 angles. All that really does is force this parallel to this. Those lines would have to be parallel by the CIA converse theorem. But beyond that, we don't have the ability to jump this over here or here because that's only true. Opposite angles are only congruent if I know this is a parallelogram. But as of right now, I don't know anything about this side or this side. And the same thing's going here too. I can't bring this 130 over here. I can't bring the 50 over here. For all we know, on the one side, I've got the 90 and 90, or the 130 and the 50, and I know it doesn't look like it, but maybe the other side's doing this. Does it have to be perpendicular right here? No. Does this have to be perpendicular? No. So just wanted to make sure. I know, like I said, I know I went back, and but we didn't really talk about a way to show or to prove a quadrilateral was a trapezoid. That's basically what we would need to know, is that we have consecutive interior angles that are supplementary, which is really the converse of this. Consecutive angles must be supplementary to force those lines parallel. Okay. So while I was thinking about it, while we were proving things were isosceles trapezoids, why don't we go through and prove that the figures are isosceles trapezoids. Okay. All right, look at that. We covered that one, actually. Those are all the properties we just talked about. We've got one figure left and one example left, so we're doing great. Last one we got here is what's called a kite. Okay. I know you've probably flown a kite. It takes on that same shape. It's a quadrilateral, a little bit longer of a definition here, that has two pairs of consecutive congruent sides. And I like this part because I think it makes it stand out that, but opposite sides are not congruent. Okay, so if I want to show, let's just do it right here. If I want to show, here's a generic kind of square looking picture, and say, hey, make this a kite. I've got a drawing of one here, like an official kite. But if I want to make this a kite, I would need to know and show that I've got right here consecutive sides that are congruent. So I've got two sides in a row right here and right here. Those are consecutive and they're congruent. And then I've got a different pair. I need two pairs of them. I got another pair here and here where it's congruent. But then if I look, opposite sides not congruent. That's what makes it a kite. Now, your traditional kite looks like this. So there's a little bit of vocab, just like we did. So I would make a little bit larger of a picture. And you're able to just kind of draw your arrows in there. So if you're working off a picture like this up here, where the congruent sides come together, those are your vertex angles. So here and here would be your vertex angles, where the congruent sides intersect. And then, not overly creative, I guess, but the non-vertex angles would be here and here, where your different side lengths come together. Okay. And the reason we need to define that is it comes up later in some of our properties here. So let's take a look at these ones I have just kind of laid out. But first one, I think it's pretty good. Just we need a kite. Sketch one and say, if a quadrilateral is a kite, if I know something's a kite, then I know that the diagonals are perpendicular. Okay, so we've seen a couple, right? Now, rhombus we've seen that with. We've seen that with a square. And now we're seeing it with a kite. So we've got three figures that we know of where the diagonals are perpendicular. Okay. That's not enough to guarantee that something's a kite. So could I ask you this question and just give you this, and that and say, what is it? I would say no. I don't think that's a fair question. I would say it's not specific enough to say that's got to be a kite, that's got to be a rhombus, that's got to be a square. I would say my answer, I guess, would be I don't know. Now, you could argue, what if I did this and this? That might be enough, at least out of the figures that we've talked about. That might be okay to say, well, obviously this can't be a square or a rhombus, because we know a square and a rhombus are equilateral. And obviously this one's got two different markings here. So by process of elimination, almost, you'd say, well, this has to be a kite. But I'm even going to hold off on that, because that doesn't necessarily have to be a kite. It could be another type of figure. So, or just kind of like a generic quadrilateral. So we'll kind of leave off proving things are kites. You almost have to see this kind of arrangement of side lengths. Okay. Whoops. Let's go here. So we probably should. I'm going to open this up here, and we'll get a picture to go with each one of these. So the diagonal connecting. So second property. This is more for kind of numbers. We'll do an example that involves some numbers here. The diagonal connecting the vertex angles is a perpendicular bisector of the diagonal connecting the non-vertex angles. So what does that mean? That's kind of a mouthful there. Let's see what that looks like. I'm going to slide all this stuff here. So on this part right here, for the note we just took there, slide up and add that, the diagonal. So if I were to draw both diagonals of a kite, let's mark it as a kite, I guess. Draw both diagonals. We already said it's perpendicular, so I guess we can add it. All right, that's going to be true for every kite. It also cuts this the diagonal from the non-vertex angles gets bisected there. So that's why we're using that term perpendicular bisector. Okay, so the perpendicular we already knew from the previous property, but it also cuts that diagonal exactly in half. Is this diagonal, whoops, I should probably use a separate set of tick marks there. Is the vertical in my picture, is this diagonal getting bisected? No. This would be this top portion, 1, 2, 3, 4, would be a different length than. So it doesn't work that way, but this one does get cut in half. Okay, so that's one additional piece. You know, could potentially show up as far as finding some segment lengths or side lengths. And then also, I don't know why I don't have room here for this, but the diagonal connecting the vertex angles is also a bisector of those angles. So this one you could almost get by with not drawing them both in. So here's my kite, my traditional kind of kite markings. And if I were to just draw this diagonal, what's going on here? Kind of because of the symmetry, I'm going to use different angle markings because I don't know that those angles actually wouldn't be congruent. But or I know that those angles wouldn't be congruent, so I'm going to use a different set, but it is bisecting those angles. So the diagonal connecting the vertex angles is an angle bisector of those vertex angles. You know, just a lot of terminology, and that just the words alone, I think, kind of can be confusing there. So that definitely make the picture. And then the last one, I think we can be a little bit more specific here. I think the picture is okay. So if we know something's a kite, then basically what we could say, the way the book says it is the exactly one pair of opposite angles are congruent. I think because we defined it as the non-vertex angles, it's always going to be the non-vertex angles would have to be congruent. So however you're making your picture, whether you turn it on its side like this one, or I want to go here and say, hey, that's a kite, those non-vertex angles here and here would be congruent. So kind of, I don't know, I would say you could argue 4 different properties of a kite. Most of these come up, notice none of them we said like, hey, that's not enough to say that this has to be a kite. So again, I couldn't give you a picture. It wouldn't be fair to me to give you a picture like this and say, hey, what is that? That doesn't have to be a kite, right? It could be, but that goes against the way we've been kind of framing some of these questions. Like, tell me what this must be. That's not a fair question right there because it's too ambiguous. That doesn't narrow it down enough. Same thing here, and same thing here. These don't narrow it down to being a kite. So, yeah, most of these properties end up showing up. We'll see in the next example as far as how we would use them more in an algebraic, find numbers, find side lengths, find angle measures sense. Okay. So last example, let's take a look. Really, the second of 2 examples. So using some of those properties, let's see what's going on here. Find the indicated length in the kite ABCD. ABCD. All right. Round answers to the nearest 10th. Uh-oh, we haven't seen that in a while. I guess if necessary. So we'll see. So let's see what we got. It's really asking us for some side lengths here. We know we're looking for BC. So we're told this is a kite. So we're going to go with that as far as being my one pair of consecutive, and this will be my second pair of consecutive congruent side lengths. So it's asking us for BC, which is also the same as AB, and then we're going to look for this side length here, which would be the same as CD. So this kind of all stems from, and we've seen this in previous lessons as well, that as soon as we get that right angle, that perpendicular, right, that was one of our properties, and we're seeing the bisector part of it with the 10 and the 10, the segment bisector, the door is open now for Pythagorean theorem. So I don't think it came up in the last notes. session, but I do believe it came up on the assigned homework problems that went with that section. So really for right now, I think, hey, let's focus on, take your pick. I guess you may as well just focus on this triangle right here and say, that's a right triangle because my property of a kite says that that's got to be a right angle. I know one of my side lengths is 12. One of my side lengths is 10. We're looking for, let's just throw an X in there. We're looking for that unknown side length. That's like an old school Pythagorean theorem, 10 squared, 8, so a squared plus b squared equals c squared. We've covered this in lesson 6.2, I believe, is when this came up for the first time this year. 10 squared plus 12 squared has to equal x squared. So we'll have to get out the calculator here. This is, we'll just do them all. This is 100. This is 144. That's 244 equals x squared. And then we can square root both sides. So I'm going to have to grab my calculator here and say x is about, that's where the rounding is going to come in. What is the square root of 244? I'm getting 15.6 if I round to the nearest tenth there. So the length of BC is about 15.6 units long. And I would know that that's true for BC and for AB. I know we already mentioned that. So about 15.6. It makes sense, I think, numbers-wise in the picture. Sure, that should be the longest side up there. It should be bigger than both 12 and 10. So I think we're okay. Let's switch it over here. Let's look for AD. So we're working with the right triangles. Yeah, I can erase this. You can obviously go back and rewatch that if you need to. I need to pick on a different triangle right here. So if we look at this triangle right here and say, I don't think I needed to make it as big, but it probably ends up being just about as big, that I've got a side 10, I've got a right angle right here, and I've got a side length of 30. We're looking again for that hypotenuse. Let's call it x again. Why not? And I can go 10 squared plus 30 squared equals x squared. Why is the x going over there? Just as a review, the x is the hypotenuse. The x has always got to be the single number, the c. So let's do it. Let's see. 100 or 100 plus 900. It's going to work out to a nice number. No. So I've got 1,000. And then we'll square root both sides. Let's see what we got here. The square root of 1,000 is 31.6 is what I got. What was I doing? I forgot what I was doing for a second. AD is about, oh no, and I cleared my calculator. What was it? The square root of 1,000? I think I said 31.6. Yep. So just a little bit longer than this piece. 31.6, but it should be longer. It's a little bit bigger here. So there we go. Two examples. It's really the same type of example of us using the Pythagorean theorem. This could switch up. Obviously we could give side lengths and maybe the 10 and the 10 and say, hey, find 12, find the length of B, whatever this is right here. I'm not saying every problem is a Pythagorean theorem problem. There could be problems involving angle measures, saying, hey, this is 90 and this is 30. Find X, find Y. And say, what? In that kite, can you do that? I'm just kind of throwing stuff out there. Obviously, if you can't tell, I'm kind of just making this up. But how would I do something like that if that's 90 and 30? Well, that comes back to knowing that these angles are the same. So I could really call that X and X and say, all right, 90 plus 30 is 120. All four of these still have to equal interior angles because it's a quadrilateral, still have to add up to 360. So 360 minus 120, we're talking 240. If I split that equally among those two angles, each one of those end up being 120 degrees for X and Y. Again, I just made that one up, but I wanted us to see it's not all Pythagorean theorem problems. This particular one was, because I knew a lot of people would maybe struggle with that one. I would kind of counting on us to be able to figure one like this out on our own. So yeah, there's kites. All right. So I think, that's pretty detailed. We went through properties of trapezoids, mid-segments of trapezoids, isosceles trapezoids, and then went through some properties of kites, all the properties of kites, and then looked at some maybe ways to apply them. So there you have it. Lesson 7.5 in the books, chapter 7 in the books. We'll call it there and say we're done. So I'll see you in future lessons.